Now for 11.6, our goal is to learn to write Lewis structures. And I've actually put a student-made video, a very good student-made video, up on Canvas, and you can take a look at that, and it goes into a little bit more animation and explanation of how we're about to do this. But we're just going to take it one step at a time here in the beginning. A Lewis structure is a representation of a molecule that shows how valence electrons are arranged. So remember, we're looking at specifically the valence electrons. That's what we're looking at when we're figuring out how something is bound to something else. We need to be able to see how they bond to other things. And remember, they only bond through their valence shell. We don't care about the inner shell because anything that's bonding with an atom doesn't care about what's going on inside. It only cares what it has immediate access to. So remember, those valence electrons are our outer shell electrons. If you look at your periodic table, remember we could determine the number of valence electrons by looking at the column of the periodic table. Starting from the left and going to column 1 and then column 2. Remember, we ignore these transition elements, and we saw in chapter 5 in our nomenclature chapter that these elements can have multiple different charges. So we're going to leave those alone for now and just look at our main group elements. So if we go over to the right, we see that in the first column of this 6 on the left, that's where charges +3 start. So we can call this +1, this is +2, this is +3. Remember, this one was plus or -4. And then we start going the opposite direction. Column 5 wants 8 electrons in its outer shell, so it's going to then accept 3. And if it accepts 3, that means it becomes negative. Then we have -2, -1, and 0. So the numbers that are in this table do not refer to the charge. They refer to the number of electrons in the valence shell. So remember, helium is just a little bit different because we're looking at it in terms of it following the duet rule rather than the octet rule, because it only wants 2 electrons in its outer shell rather than 8. But remember, this is how we label our periodic tables at the beginning of every test. We look at the charge at the top of each column and then use that to form our different compounds. But remember, these come from our valence electrons. Now, our steps for writing Lewis structures. Your first step is going to be to count the total number of valence electrons contributed by each atom, and then you're going to add them together. So for example, if I'm looking at HCl, I'm going to look at hydrogen, which has 1 electron. And then I'm going to look at chlorine, and from your table you can see that this has 7. So this is a total of 8 valence electrons. Now, what you're going to do with this is you're going to use 1 pair of those electrons to form a bond, because we have to bind them together. We have to show what's happening to hold them together. And then that takes 2 electrons, 1 from each of them. And then after this, we're left with 6. What do we do with those 6? We arrange the remaining electrons around atoms to satisfy the octet and the duet rule. So if we recall, hydrogen follows the duet rule. It's in that first row of the periodic table. It only wants a total of 2 electrons. It already has those 2 because it's got 1 that comes from hydrogen and it's got 1 that comes from chlorine. It has access to both of those electrons, so it's already happy. We have satisfied the duet rule for hydrogen, but we still need to satisfy the octet rule for chlorine. So we need to place the remaining 6 electrons around chlorine to satisfy its octet. Does chlorine now have access to 8 electrons? It does. It has access to 2, 4, 6, 8. So I can count those 2 electrons in between them for both hydrogen and chlorine because they're sharing them. Looking at something like pH 3, remember, hydrogen only needs 2 electrons. So when we're thinking about how to place these atoms in a way to make the structure, we want to be able to do this to observe hydrogen's duet rule. So for example, I can't do this. And why can't I do this? Because at this point, I've given this hydrogen access to 4 different electrons. Remember, every bond contains 2 electrons. So I've given this hydrogen access to 4 different electrons at this point. So this does not work. I can't do it in this way. Anytime I have hydrogens in a compound, I have to place them all the way around the outside of the compound. So phosphorus contributes a total of 5. Hydrogen contributes a total of 1, but there are 3. So I have to I have to add that 1 3 different times or multiply it by 3. So this gives me a total of 8 total electrons to distribute. So like we said, hydrogen has to be around the outside, because as I form bonds, I am completing that element's duet rule. I'm giving it the 2 electrons that it wants. So how many am I going to subtract at this point after making these bonds? I'm going to subtract 2 for each of the bonds that I formed, and that means 3 bonds. So I'm going to subtract 6 electrons from the 8, which means I'm left with 2. Where do those 2 electrons go? They can't go on any hydrogen, so the only place that's left for them to go is on the phosphorus. You can see here we've observed each hydrogen's duet rule. We've observed the octet rule for phosphorus. Each of these contain 2, so we had 2, 4, 6, and then we have an additional 2 on the phosphorus. So every element is happy here. For SF2, we want to count up the electrons that each element is contributing to the total. So for sulfur, we have 6. Fluorine is 7. Remember, these numbers come from the column numbers in the periodic table. Sulfur is in column 6. Fluorine is in column 7. Sulfur contributes 6. Fluorine contributes a total of 14. So I'm going to add those together to give me 20. Now, when you're setting this up, the halogens always go on the outside. They're always distributed to the outside. They are more electronegative than the others. So as a general rule, we're going to put the more electronegative elements on the outside and the least electronegative element in the center. So the first thing we have to do is form our bonds, and we use 2 electrons to form each of these bonds. So 2 here, 2 here. And since we have 2 of those, we're subtracting 4 from 20, which gives us 16 left over. Now, where are those 16 going to go? Let's start by filling the octets of the outer elements first. So this is 2, 4, 6, 8, 10, 12. And we have 2 more, 14, 16. We used all of our 16 electrons. We've made a complete Lewis structure for this compound, and it's going to look like this.